Okay, so far let's review what we have learned. Yeah, so we have learned about structure in terms of the chemical structure and then the solid crystalline structure. After that, you have learned also some part of processing, solidification, how the metal, in this case, especially for metal material, how it is made, yeah, how it is formed, and we have also discussed a little bit about imperfection that occurs inside metal, inside material when this solidification occurs, and either whether they are point defects or line defects or area defects. Then the mechanism where this imperfection spread, yeah, across the thickness of the material, we have learned as well, which is diffusion mechanism. Last week we have discussed about this diffusion. So all this solidification mechanism, imperfection, and diffusion speaks about the process of material. As we have learned in the very beginning, very early chapter of the subject, yeah, on the introduction to material by material, that from it all begins with the processing to form what structure that we want, and a particular structure will have the property that is corresponding to that structure. So we have spoken a little bit, we have discussed a little bit that, for example, even for the same material, chemically, yeah, like carbon-based material, when they have different structure, like one of the group in your class had discussed earlier, when they are in the diamond form, they will behave completely different than when they are in, for example, in the graphite form, yeah, in the graphite form or graphene form. When it is in diamond, where it forms a tetrahedral structure, then it is very hard, very difficult to deform, and even it is the hardest, known as the hardest material on Earth, and often used as cutter. Yeah, as the diamond thin film also has been used as a coating material for the tip of drilling machine. Then, but however, if it is in the form of graphite or graphene, where they only form two-dimensional structure, yeah, where it sits upon them, and so one carbon is only attached to three other carbon, while the other two electrons becomes dangling electron and forming pi molecular bonding. This will behave more as a conductor rather than insulator, but they are also mechanically fragile. So even chemically, same materials will behave differently based on their structures. And how to obtain particular structure is by controlling the processing, yeah, through, if it is metal, through the solidification, controlling the solidification process. Then afterwards, we can also control how the imperfection occurs, what type of imperfection, and how to increase the concentration of the imperfection through the thickness of the material, through a process called as diffusion. By controlling the temperature, the initial concentration at the surface, then we can control, for example, the concentration of impurities inside a host material. This is especially important when we want to make alloy. Alloy is, we can call it as solid solution. Yeah, if it were, this is basically almost same physical principle when you make a solution of, let's say, sugar inside water. It requires also kinetic energy when you stir the water, and usually when the temperature is not hot enough, it is very difficult for you to dissolve sugar inside the water, right? Similarly with, and basically that the solution is also diffusion based, but in liquid, it will be more of three-dimensional phenomena, three-dimensional diffusion. And with solid, on the other hand, usually it starts from the surface where we put the impurities on, we deposit first the impurities, And then using temperature, elevating the temperature, then we induce diffusion of that impurity through the thickness of the material, which will then can be described as two-dimensional, two-order partial differential equation. First order partial differential equation in x and in the thickness dimension and in time. Okay, so eventually after we do the processing, either to controlling the process, the solidification mechanism, or controlling the distribution to make, if you want to make alloy, or a mixture of various elements within a solid material, we need to assess the properties of the resulting material. Yeah. So how should we assess the properties here? When we speak about the properties of material, as what you have done in previous exercises in class, but properties can be many things. It can be in different domain, in different form. Yeah, you have, for example, discussed about electrical properties in one of the slide, or in the first chapter. I have discussed also about optical properties, whether a material is transparent to light, or diffuse towards light, or opaque. But still, from the beginning of material science, when it was first used or invented, until now, one of the main important properties are the mechanical properties of the material. Okay, because that is how the material interact with other materials. Even when it is applied as biomaterials to make biomedical devices or to make implants, this is one of the most important properties that we need to assess in order to assess or evaluate the suitability of certain device to be implemented for particular biomedical application. Let me give some example. For example, if you want to create artificial, let's say, bone, yeah, located to replace the femur bone, the thigh, yeah. Of course, it need to be very solid, very hard, yeah, and very rigid, very strong. But what if you are to make, for example, artificial earlobe like this, yeah, artificial earlobe. See, this one has completely, not completely, has quite considerably different properties compared to femur bone, the thigh bone. This one is more flexible. The earlobe is more flexible. Okay. What is then if you are asked to make artificial cornea, for example? Artificial cornea is, even you cannot make it very rigid, cannot make it very hard. It has to be flexible enough, yeah, so that it can be implanted easily, and also does not induce many harsh reaction from the body. So mechanical properties are important to be assessed in biomedical application, in biomedical engineering, biomedical device. So in this chapter, what you are going to learn and discuss are the various types of mechanical properties that we need to assess. Okay, and this is very important because, yeah, it represents one of the major class of properties of material that we need to evaluate and assess whenever we make implant or we make biomedical devices. So in this chapter, we will address stress and strain. Okay, stress and strain are two of the most commonly mentioned mechanical properties of material. So what are stress? What are stress and strain? And usually they are related. They are related. Why are they used instead of using load and deformation towards the material? Then elastic behavior of material, elasticity, or modulus of elasticity, or Young's modulus, based on its discovery. When loads are small, when loads are small, how much deformation occurs? What materials will deform the least, for example? Plastic behavior. At what point does permanent deformation occur? what materials are most resistant to permanent deformation. Then toughness and ductility. What are they and how do we measure toughness and ductility? Okay, so, and there are actually many other mechanical properties. We will maybe discuss them one by one. So whenever we have a material, let's say it is in the form of a solid bar like this, usually then if we zoom in until maybe few nanometer or several angstroms, then we can see how the atoms are being arranged in the crystalline structure. Yeah, of course, we are speaking about, let's say, metal, in its crystalline state. So then when we apply loading, when we apply loading like this, for example, this horizontal bar represents the horizontal, but the bottom surface of this bar. Okay. So when we apply loading, we apply mechanical loading means that we apply force towards this bar, either pushing this force towards it. For example, one end is fixed towards that end, or pulling it. Pulling it means elongate the bar downwards, yeah, to make it stretch. So when we speak about elastic deformation, the elastic region of deformation, it means that the deformation has to be reversible. What does it mean? When we apply stretch force or stretching force, stress towards the bar, or pushing force, pushing stress, the bar will deform. Deformation means that the shape of this material will deform or will change its shape. However, when we release the loading, the force loading, the stress, then when it is still in elastic deformation region, the material should come back to its original shape and form. That is what we mean with elastic deformation. Yeah. So when we apply a small load like this, and hence the bar will stretch with a elongation of delta. Delta is the what do you call it? The extension length, yeah, with a force F. In this case, then the bonds between the atoms is stretching, so there is more space between the crystalline plane, yeah, parallel or perpendicular to the force. So here, when we graph, yeah, when we draw a graph of force as a function of the delta, as a function of the extension, we will have linear elastic graph. As long as it is still in the elastic deformation, it should be in this, it should be linear. The graph should be linear. So when the force is released, then, or the process, what we call as unloading the force, then when it is elastic deformation, the material should come back to its original shape. And so the bottom part should come back to its original initial position. Okay, then, however, some material has also nonlinear elasticity. Nonlinear elasticity means that they can still come back to the when they are stretched. Yeah, when the force is being applied to that material, they will stretch also, and when the force is released, they will come back to its original condition. However, some of this material is nonlinear in the curve of the force versus delta. Yeah. Most solid material, like crystalline state material, like metal, yeah, metal, usually they have linear elastic graph of force as a function of delta. Okay, then plastic deformation, on the other hand, happens when you pull that vertical bar in this material above its linear region, yeah, above its linear region, or above, beyond its elastic region, then slip plane will occur between the crystalline plane here. The bond stretch, but not only stretch, but planes. Yeah, remember about stacking plane, yeah, A, B, C, A, B, C, A, B, C, A, B, A, B, A, B, with face center cube or hexagonal cross spec material. Okay, then it will shear. Yeah, it will shear from one plane to another. If that material is further stretched, further pulled by that force beyond its elastic deformation region. Then it will not be elastic anymore. So here, if we further extend this material, so it will go, the relationship between the force and the delta, the extension, is not linear anymore. Yeah, this is linear elastic now, not linear anymore. Then after the force of the loading, the load force is released, that material cannot come back to its original shape. Why? While the bond stretching will be relaxed, so that the distance between the plane will decrease again. However, the shear between the planes still exists. This is something which is irreversible. Yeah, when you already pull that material in the plastic region. So if we draw the graph between the force and delta, so here it is in the linear region, linear elastic region, then you pull further, you pull further, like this. Okay, then you release your pulling force. It cannot go back to its original condition here. It will have what we call as this plastic deformation. Yeah, it will come back to this region. So it will instead, the delta is not zero as its original initial condition. However, it will have this delta plastic caused by this shearing between the crystalline plane of that material. Okay, so we are speaking about force, force loading. So in material characterization, normally we don't really speak about force. What we are speaking more is about stress applied to that material. Why do we speak about stress rather than force? Because when you speak about force, let's say 5 Newton or 10 Newton, even though the same force you apply to different bar, vertical bar, however, the effect will be different if the one of the bar has smaller area compared to the second bar. Okay, it means that this engineering parameter has to be normalized against that area. So then mechanical engineer come up, or mechanical scientists come up with this engineering stress parameter. So when the material is axially being pulled, the two surfaces opposite to each other, they are moved away from each other with a perpendicular force Ft like this, then and the cross-section area is A0, then it will endure stress, an axial stress sigma, that can be calculated as to be equal as the force, the tensile force. We call it tensile if it is pulling, making the two ends of that material to move away from each other. We can call it also compressive force if we push the two ends of the material to move closer to each other. Ft divided by the cross-sectional area, the original area before loading. Okay, Ft, the tensile force, divided by A0. The unit will be in pound force per square inch. Usually we call it PSI in engineering terms, pound per square inch. Or in SI, this is British unit. However, in international system, normally now people use Newton per square meter. Or other words for this is equals to Pascal. So one Newton per square meter equals to 1 Pascal. Okay, so far so clear. So this is the stress unit, Newton per square meter or pound per square inch. Another type of stress is when the applied stress, applied force is not perpendicular to the area, to that cross-sectional area, but instead, when it makes an angle like this is a force with having an angle towards the surface area, then it has this tensile component Ft. However, it will also have this shear component Fs. Yeah, shear component means the component of the force that is in the plane of that cross-sectional area of the material. Yeah. So due to the existence of this Fs, then we also know what we call as shear stress with the symbol tau. The tensile stress usually is symbolized as sigma, while shear stress is symbolized with tau. The formula also looks similar, however, only the difference is instead of Ft, tensile force, we put Fs, shear force, in the denominator part of the formula. So tau, the shear stress, is equal to Fs divided by A0, the original area before the loading. The unit is also the same, yeah, Newton per square meter or pound per square inch. So for example, here when we have a cable, this is an example of ski lift. Yeah, maybe later when you go to Europe in the next year, and you have the chance, for example, to go to the Alpine mountain, yeah, in Switzerland or France, maybe you can do skiing. Yeah, and usually you have to go upward first to the peak of that mountain, then you do skiing from above going downward. Okay, so this is the ski lift. Yeah, it has this cable, and usually the cable is always in tension. Yeah, it is always tension, because if it is not in tension, of course, then it will be what you call it, buckling around, and then it cannot pull this wheel. Yeah, so it has to be in tension state. So the cable is in tension, yeah, with a force F. So the force F happens at the two ends. Yeah. We will learn this in biomechanics later in semester 7. Why the force there should occur in both sides. Yeah, short answer will be because they are in equilibrium. If it is not in equilibrium, then it will move. The whole thing will move to one direction. But still, since it is in equilibrium, holding the one is maybe attached to this small wheel, the other one is attached to this larger wheel. Then it is in equilibrium means for every force there has to be a reaction force of it. Yeah? That's why the force occurs at both ends. And we have A0, the cross-sectional area when unloaded. So thus the sigma, the stress, the tensile stress can be calculated as F divided by A0. The sigma also happens at both sides of the cable. In this shaft, however, this is shaft that connecting this large wheel to the lift itself, there will be also a torsion. Torsion is basically the resemblance of force, however, it occurs rotational. Yeah, torsion cause rotational motion. If force F usually cause translational motion. Yeah, maybe you have learned this a little bit in physics. Okay, so when we apply torsion M towards this rod, yeah, this rod is attached to the wheel M, and there is also this area crossing. Then the torsion will also occur at both sides of the shaft, but at opposite direction. Yeah, so hence that we have this A0 at this cross section, and Fs occurs at all this edge of this piece of the shaft. Yeah. Then the tau, the shear stress, it can be calculated as Fs divided by A0. Yeah. So note here that the tau, we can replace Fs using the moment. The moment is the moment is the one that rotating, that makes the thing rotate. Yes, this is similitude to force, however, for rotational motion. So Fs can be replaced by the m, the moment, divided by a. Yeah, remember from the formula of moment. Formula of moment is later you will learn also in semester 7, but maybe you have learned in in physics. Yeah. So here the d here is the r, the radius from the central of the shaft of this shaft, the drive shaft, to the edge, to the circumference of the drive shaft. So the Fs is replaced by m divided by r. So here then tau it will be equal to m, the moment divided by AC. AC here is the circumference area, yeah, divided by r, the radius. Okay. So stress occurs everywhere. Yeah, for example, here if we have balance rock, yeah, this is in Arcus Natural Park in, I think in US, but we also have here many rock, yeah, in Borobudur, in temple, for example. Rock are being placed on top of each other, then the rock in the middle will be in compression. Yeah, because the weight of the rock above it will push it downward, while the rock below it will have a normal force, normal reaction force pushing it upward. So that rock in the middle will be in compression state. Yeah. Similarly here with an arc, yeah, in arc bridge. Okay, this arc usually functions to hold the weight, yeah, of this bridge and the load above it, yeah, the cars, etc. This arc still is located between the two edges of that, for example, river or cliff, and it means it is under compression as well, being compressed by the two ends force, yeah, from the cliff or from the river banks. Yeah, so this is also under compressive structure. The formula for compressive stress is basically the same as tensile stress. However, usually then the sign is negative because compressive, the direction of the forces at the two ends is towards the inward of that material. Yeah, that's why the sigma is less than zero, negative. This is another example in pressurized tank. Also basically in your house, maybe you have LPG, liquefied petroleum gas. The gas inside is under compression, being compressed, right? So that the volume, many more content of gas can be preserved within a small volume of tank. It has to be under pressurized tank. Yeah, the gas inside is basically trying to push the wall, yeah, the wall of the tank, while the wall of this tank is actually compressing the gas inside. Similarly, when you are swimming, or like this fish swimming inside water, actually the water pressure also compressing your body, yeah, compressing this fish body. Yeah, so that is why this is with what we call as hydrostatic pressure, hydrostatic compression pressure, which is basically proportional to the depth of that water. So when you dive deeper and deeper, for example, inside the pool, then you will feel that pressure bigger, especially when you don't cover your ear, you feel that water, hydrostatic pressuring your eardrum, and you feel it more painful. So that's why such fish, for example, has to endure such hydrostatic compression, sigma h less than zero, because it is compression force. So what is meant now with strain? Strain is actually related with stress. When stress is later, the relationship is given by a constant called as the Young's modulus. While stress is directly related with force, stress equals to the force divided by the cross-section area. Strain, on the other hand, is related to length. Yeah. uh, the effect of a stress given to a material, the effect means here how much that the deformation occurs, is something which is also not only related to that force on alone, but also to the initial length of that material. So it is then better to express, rather than to express the deformation as an absolute length change, this delta, we express it as a ratio between that length extension delta towards the initial length L0. So this is the definition of strain. Strain is defined as epsilon here, defined as the delta, the extension, yeah, in any length unit, centimeter, meter, whatever, divided by the original length. So when we apply tensile stress, the material will undergo a tensile strain. So it means it will elongate at the same axis and the same direction as the tensile force or the tensile stress. Okay, so a delta elongation will occur since it has to be occurring in both sides of both ends of the material. So at one end, what occurs is only half of the delta. The other end will have delta over 2 as well. So since the material volume and content has to remain the same, when you extend this material at the direction uh, of the stress, then at the direction perpendicular to the stress, another dimensional change will also occur. The width, the width of that material will be contracting. So if the length is extending, when you stretch it using tensile stress, so tensile strain will occur in that material at the direction perpendicular to the stress, the width, uh, dimensional change also occur opposite to that length change. So if the length is elongated, the length increases when you apply tensile stress, the width will decrease. The original width here is WO. However, when you stretch, it becomes this green width. So it becomes smaller. So this is what we call as the lateral strain. The lateral strain is the elongation of the width, perpendicular to the direction of the stress. And since when you pull this material, the width will decrease. So it means that the direction is opposite to the magnitude of the pulling. That is why we put here minus sign. Epsilon L, the elongation, the width elongation here equals to the minus delta L, the deformation at the width, divided by WO. WO is the original width. So this is deformation of the width divided by the original width. So here you see that both numerator and denominator is of the same dimension. They have the same length dimension. That's why when we make ratio of them, they become dimensionless. That's why strain is a dimensionless parameter. Shear strain. Similarly, when you apply shear at the surface, at the same direction or line up as at the surface, like this, one of the other one is fixed, or you apply both the same. So what happens is you will have delta x only at one surface, while the other surface is you can consider it as 0. Even though sometimes you slide or you shear both surface, but you can approximate it as one of the surface of the side surface is being fixed, the other one is being slide or being sheared in the direction of the shear stress. So you will have then delta x at the surface where you apply the shear stress, while at the other side, the opposite side, you will have 0. So it will make an angle theta here, whose tangent will be equal, the tangent theta equals to delta x divided by the y. Okay, so this is called as the gamma. And similarly, like lateral strain or tensile strain, this is also dimensionless because both numerator and denominator have the same dimension, which is length dimension. How do we test tensile stress and strain here? This is the machine that we usually use. It has this motor, that will rotate this screw. When the screw is rotating, it will extend either depending on the direction. It will extend the distance between these two bars. One will be moving, the other one will be fixed. So the other one fixed to this screw, to the screw bar. Then this will create delta, the elongation. Then it has this load cell. Load cell is basically a force sensor that will measure the force loading onto this specimen. Yeah, then if you then divide it with the cross-section area of the specimen, then you will get the sigma, the stress. You will the delta you can measure from the motion of this motor in this screw, but to be accurate, you could also put an extensometer. Extensometer basically will measure the delta, the elongation or the extension or contraction of the specimen. Yeah, because the two legs are attached of this extensometer are attached to the surface of this specimen. So this is typical tensile machine. Yeah, it looks like this. If you Google tensile test machine, in Google image, you will have many images or pictures or photograph of the actual machine. So the typical tensile specimens is usually made in this kind of shape and dimension. Yeah, usually it is in the form of cylindrical. However, at both ends, it is made thicker than the middle part. Yeah, the gauge, the middle part will become the part where we will observe the stress and the strain. Yeah, so there is a gauge length here. For example, here this one has the diameter is 0.505 inch. However, the the two ends has three quarter inch of diameter. Okay, because this one will be clamped by the clamper here to two ends. Okay, so from the graph, yeah, when we do testing using this tensile test machine, what we are measuring are two parameters. The first one is the extension of the specimen, which when we divide with the original length, it becomes the tensile strain, the delta, yeah, as the explain, or the epsilon, sorry, the epsilon. The delta is the absolute extension or elongation divided by the initial length, it becomes the tensile strain. Then we are also measuring the force, F, the tensile stress or compressive stress if it will move closer towards each other. Then if you divide that force with the cross-sectional area of this specimen, then you will obtain the sigma, the tensile stress or the tensile strain. So then these two parameters can be drawn as a graph versus each other. The vertical axis here is sigma, the horizontal axis is the epsilon or the strain. Okay, the epsilon is dimensionless, while the sigma has the dimension of force divided by area square. Okay, so then when the specimen is being extended or being compressed at its elastic region, yeah, then the graph that you will obtain should be linear, yeah, because remember in elastic region that the material will deform, but when the loading is released or decreased slowly back to the zero again, then the extension should decrease also. So it means the material should come back to its original shape and form. Okay, so this is in, if it were in the elastic region, it will form a linear line. So the gradient of this line is called as E. Yeah. So here the equation of this line is sigma. This is y equals to the gradient E times the epsilon, the strain. This is what we call as Hooke's law. Remember, maybe you have learned Hooke's law for spring, normal spring, but it also applied. It can be applied also for material undergoing a tensile strain or tensile stress. The gradient here, the gradient E here is called as modulus of elasticity E, also known as Young's modulus. Okay, so this is what will occur when a material or specimen is being pulled with using a tensile test, yeah, like this. It will extend in length in the same in the direction of the force. However, in the direction perpendicular to the force, it will contract, yeah, the width will decrease. Yeah, what we call as lateral strain in the here. Lateral strain epsilon L equals to minus the width change over the original width. Okay. So the constants that relates the lateral strain, the strain that is that the axial strain, the tensile strain, with the lateral strain, the strain that occurs in the direction of the tensile force compared to the strain that occurs in the direction perpendicular to the force, they are related through a constant called as Poisson ratio. This is also a material property specific to a certain type of material. Yeah. So different material will have different Poisson ratio. So the Poisson ratio, nu, yeah, this is a Greek letter, we pronounce it as nu, equals to minus epsilon L over epsilon. Why minus? Yeah, because as we have mentioned, the lateral strain occurs at the opposite trend compared to the axial stress or axial strain. When the lateral, when the tensile strain, the strain that occurs in the same direction as the tensile stress is positive, which means that it is being stretched, then the lateral strain will become negative, yeah, because it is being compressed on the perpendicular direction. That's why we put here negative sign. So for metals, the nu is about 0.33. Ceramic is 0.25. Yeah, this shows, it means that ceramic is harder to deform compared to metals. Polymer has larger nu, yeah, so because it is easier to deform when you stretch a polymer, usually the other direction, the perpendicular direction, will deform more, yeah, in polymers compared to if you compare with in metals or in ceramics. Okay, so let's stop here for this